Hello, friends. Welcome to the sixth episode of Organic Chemistry series. In this episode, we try to elaborate on physical properties of alkanes. But before we start, if you're new to this video or even new to organic chemistry, I highly recommend that go and watch this series from the first episode. You can check it in our channel in the playlist of organic chemistry. Let's go. When it comes to physical properties of alkanes, first we need to know some details about the molecules and about the atoms when they are formed in a shape like we call them alkanes. Let's look at this shape. As you can see, we have only one carbon and 4 hydrogen atoms. But as it is shown here, the angle between this carbon and hydrogen bond and this carbon and hydrogen bond is 109.5 degrees. You may ask why. Actually, I need to refer to inorganic chemistry, which we say when carbon has 4 identical bonds, like here, hydrogen, 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 the hybridization of carbon would be sp3. And we know that when we have sp3 hybridization, the three-dimensional structure of the molecule would be tetrahedral. Okay, you may ask, what are all of these words? What does this mean? What is sp3? And I have to say, take a look at the playlist of inorganic chemistry. We discuss these details there. Okay, let's continue. So now that we know that the angle is 109.5 degrees, let's move to a new alkane, which is depicted here. In this one, we have 2 carbons, but still the angle is the same. It didn't change. But the point that I'm going to focus here is the bond length. You can see that the bond length between 2 carbons is 1.54 angstroms. However, the bond length between a carbon and a hydrogen atom is somehow around 1.1 angstrom. Actually, this distance, this bond length, would remain still or would somehow remain still when the chain of the alkane gets longer. When more number of carbons are connected together and they form an alkane. Okay, so let's go. Here you can see another molecule and another one, but with 3 and 4 carbons. You may ask, what is this zigzag form, which we can see? Actually, this zigzag form is exactly because of the hybridization and because of the structures and three-dimensional structures of the alkanes. No matter how long the chain gets, the zigzag form, the zigzag structure would remain still. Okay, now that we know the 3D structure of alkanes, it's time to get into a little more complicated concepts. Okay, we all know that matter can be seen in 3 different phases or in 3 different forms, The first form would be gas. Next one would be liquid. And the last one would be solid. So we all know that the movements of molecules are so faster in gas phase than liquid phase, and again in liquid phase than solid phase. So in the gas phase, we have so much faster movements of molecules. However, in solid, actually, we can see almost no movement or just a little. So we want to use this simple concept and talk about a really important diagram. Let's take a look at this diagram. This diagram shows three main key properties, physical properties of alkanes, which would be melting point, boiling point, and density. Okay, you may wonder why all of these trends are rising or they're showing a growth, but we want to talk about them one by one. Let's get back to this concept. We say the movement gets more and gets faster when we move in this direction. Okay, so when we have faster movements, the distance, the length, the distance between the molecules gets more. For example, we have one molecule here, and they are moving really fast in different directions. Okay, so they can't get so close to each other. So this means that in the gas phase, the distance between the molecules is more than the liquid phase, more than the solid phase. This means that in the same volume, we have less molecules of gas, more molecules of liquid, and even more molecules of solid. You can see it here. The density of alkanes rise when the number of carbons gets more. Okay, so this one is done. We now know what is happening here. What about boiling point and melting point? Okay, here we can say again, when the distance between two molecules of one matter is a lot, they tend to be in the gas phase. When the distance gets closer, they tend to move to the liquid phase and the solid phase. Okay, this trend can again be used in this diagram. As we can see, when the number of carbons gets more, the alkanes tend to be in the liquid phase and solid phase. So we can say that the first 3 or 4 alkanes, 3 carbons, 4 carbons alkanes, they are in the gas phase. More carbons, about 5, 6, 7, 8, and more, they are in the liquid phase. And when we get to the heavier alkanes, they are in the solid phase. This can be used even in boiling point when they move from liquid to solid phase, or when they move from liquid to gas phase. So to have a really quick review, we can say that all of the physical properties, all of the important physical properties like melting point, boiling point, and density have a really great growth in this diagram, which is about the alkanes. And all of these things are because of the distance between the molecules and the movements that they have in different phases. Great. Let's move to the next part. Beside this diagram, there are 3 more concepts that we need to talk about, and all of them get into one group, which is intermolecular interactions. Let's take a look at a really simple one. We start by looking at water molecule. When we take a look at water molecule, one oxygen, which is connected to 2 hydrogen atoms, we can see that this molecule is dipole. It means it has some parts with partial positive charge and some parts with partial negative charge. So when 2 water molecules get close to each other, we can have the repulsion between the same charges and the attraction between different charges. So this is when we say we have dipole-dipole interactions. But when it comes to alkanes, do you think they are dipole or nonpolar? We can see that alkanes are nonpolar, and because of this, we won't have any dipole-dipole interaction. What about others? What about hydrogen bonds? I think from basic chemistry, we can remember that to have a hydrogen bond, we need to have hydrogen, which is connected to an oxygen, which is connected to fluorine, or which is connected to nitrogen. But in alkanes, all we have is made of carbon and hydrogen. So as well as dipole-dipole interactions, hydrogen bonds does not exist in alkanes. What about London forces? When two non-polar molecules get close to each other, when they approach each other, they have a really temporary interaction with each other that makes them to be polar for a really short period of time. We can say they are temporarily polar. So in this really small interval of time, they get polar. They have a really small and weak interaction with each other, which might be repulsion or attraction. And in this case, we call this interaction London forces. We have to keep in mind that London forces are extremely weak, but they exist in alkanes, and no matter how long the chain, we can have the London forces, but they're really weak. Thank you so much. I think it's enough for today's video. Hope you had a great day and hope you found this video useful. Don't forget to subscribe for more chemistry content. This is Chem Explain.